All right, let's dive into a really wild idea that's been making the rounds. What if we solved AI's insane appetite for energy by just launching all our data centers into space? I mean, the vision is pretty cool, right? You get limitless solar power to fuel the future of AI. But is it actually genius, or is it just expensive science fiction? Let's break it down.
So this is the quote that got everyone talking. It's a super bold claim, suggesting this massive shift in how we power our most cutting-edge tech. The whole bet is that rocket launches are going to get so cheap, so fast, that building on Earth will actually be more expensive. It sounds amazing, but that's the real question, isn't it? A great vision is one thing, but you can't argue with the laws of economics and physics. So we're going to do a little back-of-the-envelope math here and see if this whole orbital dream can even get off the ground. So here's the sales pitch. And you gotta admit, it sounds pretty convincing. AI is getting hungrier for power at an exponential rate. Here on Earth, that puts a huge strain on our power grids, not to mention the environmental costs. But in space, you've got the sun, the ultimate fusion reactor, just sitting there, giving away free energy. Problem solved, right? Well, not so fast. Okay, first things first, the biggest, most obvious hurdle for anything space-related is just getting there. It costs a fortune. So let's start with the most basic piece of the puzzle. What does it cost to just launch the power source for one modern AI system into orbit? To make this real, let's imagine a single, high-density AI rack. Think of the next-gen NVIDIA systems. These things are absolute power hogs, easily chewing through 600 kilowatts to a full megawatt of power. So, to keep the lights on, we're going to need a 1 megawatt solar array. That's our starting point. And how much does a 1 megawatt solar array weigh? Well, even with modern, lightweight designs, once you add the panels, the support structure, and all the wiring, you're realistically looking at around 5,000 kilograms. That's 5 metric tons. Now, for the price tag. What's the shipping fee for that 5-ton package? Right now, if you want to launch something on a SpaceX Falcon 9, you're paying about $2,900 for every single kilogram you send to low Earth orbit. So you do the math. 5,000 kilos times almost $3,000 per kilo, and you land at a mind-boggling $14.5 million. And let me be super clear. That is just the launch cost for the solar panels. We haven't even bought the panels yet, or the AI rack itself. This is just the shipping fee to power maybe 1 or 2 servers. And look, our $14.5 million figure is actually pretty optimistic. If you decide you need a more robust, heavier structure, maybe with some redundancy, the mass easily doubles. And just like that, your launch cost skyrockets to nearly $30 million. It just goes up and up from there. That is one heck of an expensive foundation to start with. Okay, so the cost is just astronomical. But hey, let's play devil's advocate. Let's pretend launch costs drop to almost nothing. Even then, you run headfirst into a brick wall of much, much bigger problems. And these are problems you can't solve with money because they're baked into the laws of physics. First off, this whole idea of free 24/7 power is a complete myth. A satellite in low Earth orbit is actually in the dark, in Earth's shadow, for about a third of its life. So to keep your AI running, you need absolutely massive, super heavy batteries. Guess what that means? More mass, more launch cost. And on top of that, the harsh radiation in space is constantly degrading your solar panels, so your power output literally drops year after year. But honestly, all of that is small potatoes compared to the real, undisputed showstopper: heat. It's simple thermodynamics. If you have a 600 kilowatt AI rack chugging away, it is also generating 600 kilowatts of waste heat. On Earth, that's easy. We just blow air or pump water over it. But in the vacuum of space, you can't do that. See, in a vacuum, there's no air to move heat around. The only way you can get rid of heat is to radiate it away as infrared light. It's called radiative cooling, and the key thing you need to know is that it is wildly, spectacularly inefficient compared to the cooling systems we have down here. So that brings us to the killer question. If you have to get rid of 600 kilowatts of heat from a single AI rack using only this incredibly inefficient radiation method, just how big does your cooling system, your radiators, have to be? The answer is around 1,500 square meters. No, that is not a typo. 1,500 square meters of radiator surface area, just to keep one single server rack from melting itself into a useless slag of metal. To put that into perspective, that's roughly the size of an American football field. I want you to just picture that for a second. You have to launch,
deploy, and operate a fragile football field-sized structure in orbit just for the cooling system, for one computer. The sheer scale is just completely absurd. But let's keep the thought experiment going. Let's say you solve the cost, you solve the power, and you somehow invent a magic football field-sized radiator. You still have one final, completely unavoidable deal breaker: latency. The speed of light is not on your side. Think about it. A signal has to travel from you, on Earth, all the way up to the satellite, and then all the way back down. Even in a perfect, best-case scenario, that round trip is going to take you somewhere between 40 and 100 milliseconds. Compare that to a data center here on the ground, where you're looking at under 10 milliseconds. It's at least 4 to 10 times slower. So why does that matter? Well, for pretty much every AI application that makes money, we're talking search engines, virtual assistants, high-frequency trading, even just a website that feels fast, that kind of delay is an absolute killer. It's just too slow. The service feels sluggish and unresponsive. It's a non-starter. And you know what? It gets even worse. Remember, this satellite is whipping around the Earth every 90 minutes. That means your connection to this data center is not constant. You might get a few minutes of access while it's overhead, and then poof, it's gone. It just flies over the horizon, and you're completely disconnected until it comes all the way back around an hour and a half later. This isn't a cloud service, it's a drive-by data center. So let's put it all together: the insane cost, the football field-sized radiators, the terrible latency, and the fact that it's only online for a few minutes at a time. If you were going to honestly pitch this as a product, what would you even call it? This quote just nails it perfectly. Even if you could magically make it cheap, you're left with a service that you can use for 2 minutes, and then you have to wait an hour and a half to use it again. For any kind of real-time application, it's just fundamentally broken. Which leads us to what has to be the most accurate, if a little snarky, marketing slogan for this whole idea: introducing orbital AI. It's compute so scalable, it periodically leaves the planet. It's the perfect summary of a futuristic dream getting completely wrecked by practical reality. And really, that's the big takeaway here. We love to look to space, to the final frontier, to solve our grand challenges. But maybe, just maybe, when it comes to the raw, brute force power needs of modern AI, the real final frontier isn't up there in orbit. It's down here, in a boring old basement, right next to a very cold river. Thanks for watching!